This is why we will never truly leave Earth. This is the reason why we will never abandon Earth. Every night, millions of people look up at the starry sky and dream of other worlds. Elon Musk promises cities on Mars by the year 2050. NASA is designing permanent lunar bases. Jeff Bezos speaks of floating space colonies. But there is a truth that no one wants to utter aloud, an uncomfortable reality that contradicts all these brilliant promises. Humanity will never truly abandon this blue planet. This is not about pessimism or lack of imagination. It is about fundamental physics, about implacable biology, about mathematics that do not lie. For decades, we have fed a collective fantasy about becoming a multiplanetary species, about scattering human civilization across the cosmos like seeds in the wind. This illusion has shaped our popular culture, directed trillions of dollars in investment, and inspired entire generations of scientists and engineers. But what if it was all a beautiful mirage? What would happen if we discovered that the barriers to leaving Earth are not technological but fundamental? What would it imply for our species to accept that this small world, this fragile sphere of rock and water, is the only home we will ever have? The question is not whether we have the technology to colonize other worlds. The true question is much deeper, much more unsettling. Can human life, as we know it, exist anywhere else in the universe? The answer will completely change your perspective on our place in the cosmos. Before continuing this journey towards an uncomfortable yet liberating truth, I invite you to subscribe to Scientia Nocturna. Here we explore the questions that other channels avoid, the truths that transform how we understand our universe. Because sometimes, the most important science is not the one that makes us dream of distant worlds, but the one that helps us to value the world beneath our feet. During the upcoming chapters, we will systematically dismantle each of the pillars upon which the fantasy of space colonization is built. We will discover that Earth's gravity is a prison from which we will never truly escape, that the Earth's magnetic field is an invisible shield without which cosmic radiation would destroy our DNA in months. That liquid water, that element so common on our world, is virtually non-existent in the rest of the solar system. That our perfect atmosphere is impossible to replicate artificially. That our own bodies were shaped by millions of years of evolution, specifically for this planet, and only for this planet. We will explore the brutal economics of space, where keeping a single person alive costs more than feeding thousands on Earth. We will reveal why all proposed space bases would be eternally dependent on terrestrial supplies, never true, self-sufficient colonies. And finally, we will arrive at a conclusion that may seem sad, but which is profoundly liberating. Because you see, understanding that Earth is our only possible home is not a limitation. It is an invitation to gratitude, an urgent call to action. If this is the only world that can sustain us, then protecting it is not a political option or a personal preference. It is literally the only guarantee of our species' survival. Settle in, take a deep breath, and prepare to see the universe and our place in it in a completely new way. This is the story of why we will never leave Earth, and why that is perfectly fine. Imagine for a moment that you are an ant at the bottom of a deep well. The walls are smooth, almost vertical, and extend hundreds of meters above your head. Up high, very high, you can see a circle of light, the world outside. Now, imagine trying to escape. Every centimeter you climb requires a monumental effort. Each upward step consumes energy that you can barely generate. And if you slip, if you lose your grip, even for an instant, you fall back to the bottom, forced to start over. This is exactly what it means to live at the bottom of Earth's gravitational well. Gravity is not just that force that keeps your feet on the ground, or that makes objects fall. It is an energetic prison, a physical barrier that requires astronomical amounts of energy to overcome. And here is the uncomfortable truth that no one in the space industry wants to openly admit. The energy required to escape this gravitational well makes mass space colonization mathematically impossible. Let us consider the cold, ruthless numbers. To put a single kilogram of mass into low Earth orbit, you need approximately 30 megajoules of energy. That is equivalent to the energy contained in almost 1 liter of gasoline, burned with perfect efficiency. But here is the problem. Rockets are not perfectly efficient, not even remotely. In reality, to put that kilogram into orbit, you need to burn approximately 100 times that amount of fuel. When you consider all the infrastructure, the weight of the rocket itself, the tanks, the engines. An adult human weighs approximately 70 kilograms. But you cannot simply launch a naked human into space. You need a spacesuit that weighs another 50 kilograms. Food and water for the journey, another 100 kilograms if you plan a trip of several months. Survival equipment, tools, medical supplies, another 200 kilograms, and that is not counting the spacecraft itself, which weighs in tons. To send a single person to Mars with everything necessary to survive the journey, we are talking about launching approximately 100 tons of material from the Earth's surface. The required energy is equivalent to the total electrical production of a small city for several days, and that is just one way. If you want them to return, double those numbers. Now think about what it means to colonize another world. We are not talking about sending a dozen brave scientists on a prestige suicide mission. We are talking about relocating thousands, eventually millions, of people. We are talking about sending all the infrastructure necessary to sustain human life. Power generators, mining equipment, factories, greenhouses, hospitals, laboratories. Every bolt, every cable, every solar panel has to be ripped from the bottom of this gravitational well. The mathematics are brutal. To establish a Martian colony of barely 1,000 people, comparable to a small village, you would need to launch approximately 100,000 tons of equipment and supplies. That would require thousands of heavy rocket launches, consuming more energy than the annual electrical production of several developed countries. And all this, assuming nothing goes wrong, that every launch is perfectly successful, that there are no accidents or failures. But wait, you will say, technology improves, rockets become more efficient. SpaceX has developed reusable rockets that reduce costs. Surely over time we will overcome this barrier, right? Here is the fundamental problem that no amount of technological innovation can solve. We are not talking about engineering. We are talking about basic physics. The escape velocity of Earth, the minimum speed necessary to break free from its gravity, is 11 kilometers per second. That is 40,000 kilometers per hour. No matter how advanced your technology is, you need to accelerate mass to that speed. And accelerating mass requires energy. The equation is simple. Kinetic energy equals 1/2 mass multiplied by velocity squared. You cannot negotiate with the laws of physics. You cannot find a shortcut around the conservation of energy. Even if we develop the most efficient rocket theoretically possible, one that converts fuel into motion with 100% efficiency, something that violates the laws of thermodynamics, you would still need massive amounts of energy for every kilogram you send into space. And here comes the part that truly destroys the fantasy of mass colonization. Not only do you need energy to leave Earth, you also need energy to leave the gravitational well of any other celestial body you go to. Mars has approximately 1/3 of Earth's gravity. Sounds manageable, right? But that means leaving Mars still requires reaching speeds of 5 kilometers per second. And on Mars, there are no vast reserves of rocket fuel waiting to be extracted. You would have to manufacture the fuel there, which requires massive energy, infrastructure that, guess what, has to be sent from Earth. Some visionaries propose creative solutions, space elevators, cables that extend from the Earth's surface to geostationary orbit, allowing payloads to be lifted without rockets. It sounds ingenious until you consider the necessary materials. You would need a cable, 100,000 kilometers long, capable of supporting its own weight, plus the load it transports. No known material exists with the necessary tensile strength. Carbon nanotubes, the strongest material we have developed, do not even come close to what is required. and producing enough to build a space elevator would take the industrial production of all humanity for centuries. Others talk about nuclear propulsion engines, solar sails, electromagnetic cannons. Every proposal has fundamental problems. Nuclear engines still need reaction mass to push. Solar sails are incredibly slow and only work far from planets. Electromagnetic cannons would subject any human passenger to accelerations that would turn their internal organs into mush. The reality is this: Earth's gravity is not just a technical inconvenience, it is a fundamental energetic barrier that defines the practical limits of human expansion. We can send some people into space, maintain small stations, conduct scientific missions. But the idea of moving human civilization beyond this planet clashes with the relentless realities of physics. Think of all the energy that humanity currently generates, all the electricity from all the power plants, all the fuel burned in all the vehicles, all the captured solar energy, all the wind converted into electricity. Now, imagine dedicating a significant portion of that energy, say 10%, exclusively to launching things into space. Sounds like a lot, right? With that 10% of our global energy production, we could put approximately 1 million tons into orbit each year. 1 million tons sounds impressive until you put it into perspective. The International Space Station weighs 420 tons and houses 6 people. Generously extrapolating, 1 million tons could sustain a space population of perhaps 10,000 people. That is less than the population of a small city. And that is dedicating 10% of all global energy, energy that is currently used to power hospitals, factories, homes, transportation. The gravitational prison holds us captive, not for lack of will or imagination, but because of the cold arithmetic of energy and mass. Every human we send into space represents energy that is not used to improve life here on Earth. Every ton of equipment launched is energy that does not power schools, does not purify water, does not produce medicines. And this is perhaps the cruelest irony. To sustain even a small population in space, we would need the resources of the entire terrestrial civilization, functioning perfectly, without interruptions, without collapses for generations. Space colonization would not free us from dependence on Earth. It would make us more dependent than ever on maintaining terrestrial civilization functioning at maximum capacity. Gravity keeps us here, not as prisoners, but as permanent residents of the only known place in the universe where life can flourish without constant titanic effort. It is a lesson in humility. We are creatures of this world, shaped by it, sustained by it, and fundamentally incapable of replicating its conditions anywhere else, without investing resources that we simply do not have and never will. There is something protecting us at this very moment, something invisible, something you cannot see, touch, or feel, but without which you would be dead in a matter of months. It is not the air you breathe, although that is also critical. It is not the water you drink or the food you eat. It is something much more fundamental, something so ubiquitous that humanity was not even aware of its existence until just a few centuries ago. It is the Earth's magnetic field, and it is the reason why complex life can exist on this planet, but not anywhere else in our solar system. Imagine you are standing under an invisible cascade of bullets, billions of microscopic projectiles falling from above at speeds close to the speed of light. Each one capable of passing through your body, tearing your DNA, destroying the cells that keep you alive. But they never reach you because there is a shield over your head, an invisible force field that deflects these bullets, that curves them around you, that protects you without you even knowing it. That shield is real, and those bullets are too. The sun is not the kind, generous star it appears to be from here. It is an uncontrolled nuclear reactor, a ball of scorching plasma that spews deadly radiation in all directions. Charged particles accelerated to relativistic speeds, high-energy protons, electrons, naked atomic nuclei, all shooting out from the sun in a constant stream called the solar wind. And beyond the sun, From the depths of interstellar space come cosmic rays, particles accelerated by distant supernovae, by black holes, by cataclysmic events that happened millions of years ago in distant galaxies. This radiation is mortally effective at one thing: destroying complex organic molecules. Your DNA, that elegant double helix that contains the instructions for building and maintaining your body, is particularly vulnerable. When a high-energy particle hits a strand of DNA, it can break it completely, it can cause mutations, it can kill the cell instantly, or even worse, it can damage it in ways that make it cancerous. Your body has repair mechanisms for DNA damage. They are remarkably efficient for the normal levels of radiation we experience on Earth. But those levels are extraordinarily low, precisely because the Earth's magnetic field deflects 99.9% of the cosmic radiation before it reaches the surface. The Earth's magnetic field extends for thousands of kilometers into space, forming a protective bubble called the magnetosphere. The charged particles of the solar wind are trapped in this bubble, deflected towards the poles, where they create the beautiful aurora borealis and australis. Those dancing lights in the night sky are not just pretty, they are visible evidence of billions of lethal particles being diverted away from us, channeled into the upper atmosphere where they cannot harm us. Now, let us consider what happens when you step out of the protection of this shield. Astronauts on the International Space Station, orbiting just 400 kilometers above the surface, are still within the magnetosphere. Even so, they experience radiation levels approximately 10 times greater than on the Earth's surface. During a typical 6-month mission on the station, an astronaut receives as much radiation as they would receive in several years on Earth. This increases their lifetime cancer risk by approximately 3%. 3% may not sound like much, but it is the equivalent of smoking half a pack of cigarettes a day for those 6 months, and that is within the partial protection of the magnetosphere. Now, imagine traveling beyond it. The journey to Mars takes approximately 9 months, using current propulsion technology. During those 9 months, you would be completely exposed to the solar wind and cosmic radiation without any magnetic protection. NASA calculations estimate that an astronaut on a round trip to Mars would receive approximately 60 times the annual radiation dose permitted for nuclear workers on Earth. 60 times. The consequences are devastating. First, there is acute radiation. Enough exposure in a short period can cause radiation, sickness, nausea, vomiting, extreme fatigue, damage to the immune system. But that is just the immediate effect. The real damage is cumulative and long-term. Every cell in your body would be under constant bombardment. The cells of the digestive system regenerate quickly and are particularly vulnerable. The cells of the brain tissue, which do not regenerate, would accumulate permanent damage. Recent studies suggest that cosmic radiation can cause cognitive decline, memory problems, difficulty concentrating. Astronauts traveling to Mars could return with permanent brain damage. And then there is cancer. It is not a question of if you will develop cancer after such exposure, but when and how many different types. Leukemia from radiation damaging the bone marrow, lung cancer from inhaled particles, thyroid, skin, or colon cancer. The risk of developing at least one fatal cancer after a trip to Mars is estimated at more than 30%. 30% chance of dying from radiation-induced cancer. Those are not risks that a civilization can accept for mass colonization. But surely, you will say, we can build protection, we can shield spaceships against radiation, right? Here is the problem. Cosmic radiation is incredibly difficult to block. We are not talking about X-rays or gamma rays that can be stopped by lead sheets. We are talking about high-energy particles, heavy atomic nuclei, traveling at a significant fraction of the speed of light. To stop them effectively, you need mass, a lot of mass. Calculations suggest that you would need approximately 2 meters of water or 1 meter of solid metal, completely surrounding the habitat, to reduce radiation to terrestrial levels. Imagine a spaceship where every wall is a water tank 2 meters thick. The weight would be astronomical. A ship large enough to house half a dozen astronauts would require hundreds of additional tons just in shielding. And remember the previous chapter. Every kilogram you send into space requires enormous amounts of energy to get out of Earth's gravitational well. Worse yet, when high-energy particles hit dense shielding material, they can create secondary radiation, sometimes more dangerous than the original radiation. It is like trying to stop bullets and creating shrapnel fragments in the process. Some specialized materials, such as certain hydrogen-rich plastics, are better at this than metal, but still require massive thicknesses to be effective. Now, let us consider not a temporary trip, but a permanent colony on Mars or the Moon. These bodies do not have significant magnetic fields. The Moon has none at all. Mars has only weak, localized vestiges of what was once a global magnetic field, lost billions of years ago when its core cooled. This means that any colony on the surface would be under constant radiation bombardment. Every time you leave the habitat, every moment exposed on the surface, you would be accumulating damage to your DNA. The only solution would be to live completely underground, buried under meters of rock or Martian regolith to provide shielding. Imagine the existence, a completely subterranean life, never seeing the sky directly, never feeling the wind, always aware that a few meters of rock are the only thing between you and slow death by radiation. And yet you would have to go out occasionally to maintain equipment on the surface, to extract resources, to repair damaged systems. Each outing would be a calculated risk, a gamble against cancer. And here is the truth that no one wants to say out loud. You cannot terraform a magnetic field. You can dream of turning the atmosphere of Mars into something breathable, with melting the polar caps to create oceans, but you cannot simply switch on a planetary magnetic field. The magnetic fields of planets like Earth are generated by dynamos in molten cores of liquid metal. Earth's core is a sphere of iron and nickel, the size of the Moon, heated to thousands of degrees, rotating and creating massive electric currents. That is what generates our magnetic field. You cannot build that artificially. You cannot restart the dead core of Mars. Some fantastical proposals suggest placing a giant magnetic satellite between Mars and the Sun to create an artificial magnetic field. But the energy required to maintain such a device would be equivalent to the energy production of the entire terrestrial civilization. And it would only work as long as you kept it active, requiring constant supplies of energy and maintenance from Earth. The sad reality is that the Earth's magnetic field is not just a convenience, it is a fundamental condition for complex life. Without it, radiation would slowly sterilize any ecosystem. Mars probably had a magnetic field 4 billion years ago. It probably had oceans, a dense atmosphere, perhaps even microbial life. And then, its core cooled, the magnetic field collapsed, and the solar wind slowly stripped its atmosphere over 1 billion years. What remains is a radioactive desert. That is our future on any world without a magnetic field. Buried survivors living in burrows, every generation accumulating more genetic damage, more mutations, more cancer. It is not colonization, it is barely survival, and only as long as Earth can continue sending supplies, replacement equipment, medicines that could not be produced locally. The Earth's magnetic field is an extraordinarily rare gift. It is the result of specific conditions. A planet of the right size, with the right composition, at the right distance from its star, with a core that remains molten after 4.5 billion years. It is a convergence of factors so improbable that it may not be repeated anywhere else in the solar system, perhaps even anywhere else in the nearby galaxy. And we take it for granted. We live our lives completely unaware of the invisible shield that makes every moment of our existence possible. Only when we try to leave its protection, only when we venture into the hostile vacuum beyond, do we truly understand how special, how irreplaceable, how absolutely essential this magnetic field is. It is not just that it is difficult to live without it. It is that life, as we know it, complex life, with brains that can think and bodies that can build civilizations, is fundamentally impossible without this protection. The magnetic field is not a luxury, it is an absolute requirement, and it only exists here, on this planet, in this one place in the solar system, where we can exist without being slowly destroyed by the cosmos itself. Open your kitchen faucet, watch the clear, cool water flow, apparently inexhaustible. Fill a glass, drink it, without thinking. It is so common, so abundant, so ordinary, that we barely pay attention to it. Flowing rivers, oceans that cover 70% of the planetary surface, clouds that bring rain, snow that melts in spring. Water is everywhere, except that it is not. Leave this planet, and liquid water disappears completely. Not only is it scarce, not only is it difficult to find, it is virtually non-existent throughout the entire solar system. And this simple absence makes space colonization go from extremely difficult to fundamentally impossible. Because without liquid water, there is no life, no agriculture, no industry, no civilization, and certainly no way to sustain human populations away from Earth. Let us start with a fundamental chemical truth. Liquid water can only exist within a very narrow range of conditions. You need a temperature between 0 and 100 degrees Celsius at normal atmospheric pressure. Change the pressure, and that range changes, but not by much. Too cold, and it freezes into ice. Too hot, and it evaporates into steam. Very low pressure, and it cannot exist as a liquid at all, sublimating directly from ice to vapor. Earth has liquid water in abundance, because we occupy a perfect temperature zone around the sun, and because we have an atmosphere with the correct pressure. It is an extraordinary coincidence of factors, and it is not repeated anywhere else nearby. Let us consider the other planets of our solar system. Venus is too close to the Sunday. Its surface reaches 470 degrees Celsius. Any water it ever had evaporated eons ago, decomposed into hydrogen and oxygen by solar radiation, and the hydrogen escaped into space. Venus is an arid hell. Mercury is even closer, even hotter. During the day, it reaches 430 degrees. It does not even have a significant atmosphere. Water is impossible. Mars is too far away and too cold. The average temperature is -80 degrees Celsius. But more importantly, its atmosphere is so thin, less than 1% of Earth's pressure, that liquid water cannot exist stably on the surface. If you placed a cube of water on the Martian surface, it would start to boil and freeze simultaneously, sublimating directly into vapor that would disperse in the thin atmosphere. In a matter of minutes, nothing would remain. The gas giants, Jupiter, Saturn, Uranus, Neptune, do not even have solid surfaces, much less accessible liquid water. There is water there, in the form of ice, mixed with their atmospheres, but it is hundreds of kilometers deep, under pressures that would crush any spaceship like a soda can. What about the moons? There are dozens of them in the solar system. Surely some have water, right? They have ice, a lot of ice. Europa, one of Jupiter's moons, has a global ocean beneath kilometers of surface ice. Enceladus, one of Saturn's moons, has geysers that eject water into space from a subterranean ocean. Titan has lakes of liquid methane on its surface, and probably deep liquid water beneath its icy crust. These are exciting discoveries for astrobiology, possible homes for microbial life, but they are completely useless for human colonization. Water buried under kilometers of solid ice at hundreds of degrees below zero, on moons, without significant atmospheres, orbiting giant planets billions of kilometers from Earth, is not accessible. You cannot simply drill down to it. You cannot pump it to the surface. The energy required to melt the ice, to keep it liquid, to process it into potable water, is astronomical. Here is the cruel irony. There is water in the solar system, perhaps as much as in the terrestrial oceans, counting all the ice in the comets, in the asteroids, on the distant moons, but it is in the wrong form, in the wrong places. at the wrong temperatures. It is like dying of thirst in the ocean. The water is everywhere, but you cannot drink it. Let us return to Mars, because it is the most common goal of colonization fantasies. Mars has water. The polar caps contain water ice mixed with carbon dioxide ice. There is subsurface ice detected by orbital radar. Perhaps enough water to fill an ocean if you could melt it all. This sounds promising until you consider the practical reality of accessing it. First, you have to find the ice. It is not uniformly distributed. It is concentrated at the poles and at certain latitudes. Then, you have to excavate it. The Martian regolith is like frozen cement, compacted dust, mixed with ice, at temperatures of 60 degrees below zero. You need heavy mining equipment, energy to power it, heat to melt the ice once extracted. Let us assume you overcome these obstacles. Now you have dirty ice. You need to purify it. Martian water is likely contaminated with perchlorates, poisonous salts that are common in Martian soil. You need complex filtration systems, chemical processes to remove toxins. All of this requires energy, specialized equipment, constant maintenance, and once you have pure water, you still need to store it in an environment where it naturally wants to freeze or evaporate. You need pressurized and heated tanks, piping systems that will not freeze, redundancy for when something inevitably fails. Compare this with Earth, where you simply dig a well and the water flows up by itself, where rain fills reservoirs for free, where rivers transport billions of liters without any human effort. The difference is not one of degree, but of fundamental category. But water is not just for drinking. It represents something much deeper. It is the basis of all biological and industrial economy. Do you want to grow food on Mars? Every plant needs water, a lot of water. A single human needs approximately 2,000 liters of water a year just to grow enough food to survive. That is assuming perfectly efficient greenhouse agriculture with 100% water recycling, something we have never achieved, even on Earth. A colony of 1,000 people would need 2 million liters of water just for agriculture, and that is not counting drinking water, hygiene, or industrial processes. Do you want to manufacture things on Mars? Practically, every industrial process requires water. Cement production, you need water. Metal refining, you need water. Plastic manufacturing, you need water. Cooling electronic equipment, you need water. Water is not one resource among many. It is the fundamental resource upon which all other processes depend. You want to generate breathable oxygen. The most efficient way is electrolysis of water, dividing it into hydrogen and oxygen. Every human breathes approximately half a liter of oxygen per minute. Producing that from water requires decomposing approximately 750 liters of water per person per year. And that is with perfect efficiency that you will never achieve in reality. Now multiply all these requirements by a population of thousands or millions. The amounts of water needed are truly astronomical, and everything has to be extracted, melted, purified, and distributed in a hostile environment that actively tries to freeze it or evaporate it at every moment. The standard proposal is to recycle water with the highest efficiency possible. The International Space Station recycles approximately 90% of the water, including recovering water from urine and air humidity. It is an impressive feat of engineering, but that 10% loss accumulates. You need constant resupply, and recycling systems are complex, require constant maintenance, have components that fail, and need replacement. On Earth, when a water purification system fails, you can temporarily get water from other sources while you repair it. On Mars, if your recycling system fails and you cannot repair it immediately, people start dying of dehydration in days. There is no natural backup, no nearby river from which you can draw water temporarily. Every liter must be actively produced and maintained in a liquid state. This absolute dependence on technological systems that cannot fail creates a fundamental fragility, a single point of failure, a critical component that breaks with no available spare. and the entire colony faces collapse. And remember, spare parts have to come from Earth. A 9-month journey in the best launch window that only occurs every 26 months. Imagine living like that. Every drop of water you drink, that you use to wash yourself, that feeds your crops, had to be actively mined, melted, purified, and protected against an environment that constantly tries to destroy it. Every system that makes this possible is an existential risk. The constant anxiety of knowing that your survival depends on machines that could fail at any moment. Contrast this with Earth, where water simply exists, where the hydrological cycle works automatically, evaporating water from oceans, transporting it in clouds, dropping it as rain, filtering it through the soil, accumulating it in aquifers. It is a planetary life support system that works without human intervention, that has worked for billions of years, that will continue to work no matter what we do. This is perhaps the deepest lesson about water. It is not just a resource, it is an indicator of fundamental habitability. Planets with abundant and stable liquid water flourish. Planets without it are dead deserts, where survival requires constant heroic effort. Some optimists point out that finding water on Mars makes colonization possible. Technically, yes, just as it is technically possible to survive in Antarctica. We can maintain research stations there, with constant support from the rest of the world. But no one seriously talks about colonizing Antarctica, about moving millions of people there, about building self-sufficient civilizations. Why? Because it is too hostile, too cold, too remote, requires too much constant external support. And Antarctica is a paradise compared to Mars. It has breathable air. It has normal atmospheric pressure. It is only hours away from civilization centers, and yet it is considered too inhospitable for real colonization. Mars does not have breathable air. It does not have usable atmospheric pressure. It is months away from any help, and its water is frozen underground, requiring constant industrial effort to access. How can anyone seriously think that colonizing Mars is viable, when we do not even consider colonizing much more hospitable places on our own planet viable? The answer is that the fantasy of space colonization is not based on rational viability analysis. It is based on romantic narratives about the frontier, about exploration, about human destiny among the stars. They are beautiful stories, but they clash with the simple chemical reality of water. Without liquid water, abundant and accessible, there is no colonization. There is only temporary survival, dependent on supply lines from Earth, always on the verge of collapse. And liquid water, abundant and accessible, only exists in one place in the solar system, here on this blue planet, where entire oceans await beneath clouds that never stop renewing themselves. There is a children's story about a girl named Goldilocks, who enters the house of 3 bears. She tastes 3 bowls of porridge. One is too hot, another too cold, but the third is just right. She tries 3 chairs, one too big, another too small, but the third is perfect. It is a story about finding the right balance. Astronomers borrowed this concept to describe something much deeper: the habitable zone around a star, the zone where a planet is not too close to the sun to be a scorching hell, nor too far to be a frozen desert, the zone where the temperature allows liquid water to exist, the Goldilocks zone. And Earth is not just in that zone, it is exactly in the center of it, in the perfect sweet spot. This is not a lucky accident. It is the fundamental reason why we are here, and it is the reason why we cannot be anywhere else. Let us consider what temperature really means. It is not just a sensation of heat or cold. It is molecular energy in motion. It determines whether atoms remain bonded in rigid solids, whether they flow as liquids, whether they disperse as gases. It determines which chemical reactions can occur and which cannot. It determines whether life based on carbon chemistry is possible. Life, as we know it, requires a surprisingly narrow temperature range. Too cold and biochemical reactions slow down until they stop. Cell membranes become rigid. Ice crystals puncture cells from within. Below approximately -20 degrees Celsius, complex life cannot actively function, only survive in states of suspended animation. Too hot, and proteins denature, losing their shape and function. DNA breaks down. Above approximately 50 degrees Celsius, most forms of complex life die quickly. Some extremophiles can survive higher temperatures, but they are simple, highly specialized organisms, not the kind of complex ecosystems needed to sustain human civilizations. This gives us a viability window of approximately 70 degrees Celsius. It is a ridiculously narrow range compared to the temperatures that exist in the universe, which range from near absolute zero, -273 degrees, up to trillions of degrees in the interior of stars. Earth maintains its average temperature at approximately 15 degrees Celsius, perfectly in the middle of the complex life zone. And it maintains this average with remarkable stability, varying only a few degrees over periods of millions of years. This stability is not accidental. It is the result of multiple feedback systems that regulate the climate. Oceans that absorb and redistribute heat, carbon cycles that adjust the greenhouse effect, clouds that reflect sunlight. Now, let us look at our planetary neighbors and see how far they are from this perfect zone. Venus is 108 million kilometers from the Sun. Earth is 150 million. Only 42 million kilometers of difference, less than 30% closer. It seems like a small difference, but the consequences are catastrophic. Venus receives approximately double the solar energy per square meter as Earth. That extra energy was enough to trigger a runaway greenhouse effect eons ago. Today, the surface temperature of Venus is 470 degrees Celsius, hot enough to melt lead. The atmosphere is pure carbon dioxide, at 90 times the terrestrial pressure. Sulfuric acid reigns in the high clouds, evaporating before it reaches the ground. Soviet probes that landed on Venus in the 1970s lasted less than 2 hours before being crushed, melted, and corroded to death. There is no way to cool Venus. Some propose putting giant parasols in space between Venus and the Sun to block some of the sunlight, but the heat is already trapped in that atmospheric oven. It would take thousands of years of cooling, even if you could block all the sunlight, and maintaining continent-sized structures in space would require resources that we cannot even imagine. Now look in the opposite direction. Mars is 228 million kilometers from the Sun, 50% farther than Earth. It receives only 43% of the solar energy per square meter that we receive. The result is a frozen world, with an average temperature of -63 degrees Celsius. Summer days at the Martian equator can reach 20 degrees Celsius at noon. It sounds almost pleasant until you realize that those same nights fall to -70 degrees, a temperature range of 90 degrees in a single day, and that is at the equator during summer. In higher latitudes in winter, temperatures drop to -125 degrees Celsius. The carbon dioxide in the atmosphere literally freezes and falls as snow. Living on Mars would mean existing in a permanent freezer. Every habitat would require constant heating. Every spacesuit would essentially be a complete life support system, protecting against the deadly cold, even before lack of air or low pressure reaches you. And heating Mars is not a realistic option. Some proposals suggest releasing greenhouse gases into the Martian atmosphere to initiate artificial global warming. But Mars has so little atmosphere to begin with, less than 1% of the terrestrial pressure, that even doubling or tripling it would not create a significant greenhouse effect. You would need to increase the atmospheric mass by a factor of 100, releasing trapped gases in the soil and the polar caps. Calculations suggest that even if you could release all the carbon dioxide from the Martian polar caps, you would only increase the atmospheric pressure to approximately 2% of Earth's. Not enough to walk without a pressurized suit. Not enough to create a greenhouse effect that would significantly heat the planet. And the process would take centuries of sustained industrial effort. But the problem is more fundamental than just the distance to the Sun. It is also about how a planet retains or loses heat. Earth has a dense atmosphere that acts like a blanket, trapping heat during the night. It has massive oceans that act as thermal batteries, absorbing heat during the day and releasing it during the night, softening temperature fluctuations. Mars has no oceans. Its thin atmosphere provides almost zero insulation. The result is those wild temperature oscillations. You cannot create oceans on Mars without first creating a dense atmosphere. You cannot create a dense atmosphere without a massive source of gases. There is no massive source of gases available on Mars. It is a circular problem with no practical solution. Even if you could magically give Mars a terrestrial atmosphere and oceans, there is another problem. The lack of a strong magnetic field means the solar wind would slowly strip that atmosphere over timescales of millions of years. It is exactly what happened to ancient Mars. Any atmosphere you created would be temporary in geological terms, requiring constant replenishment. Now let us consider the moons of the outer planets: Europa, Enceladus, Titan. Some have oceans beneath their icy surfaces. Some might harbor microbial life. But they are so far from the Sun that surface temperatures are 150, 180, up to 200 degrees below zero. Sunlight is so weak that it is virtually useless for power generation. These worlds are submerged in a perpetual night of deadly cold. Maintaining human life there would require massive energy just for basic heating. Where would that energy come from? You cannot use solar panels effectively so far from the Sunday. You would need nuclear reactors, many of them running constantly, requiring fuel that would have to be sent from Earth and backup systems. Because if your heat source fails, when you are on a world 180 degrees below zero, you die in minutes as your habitat freezes. The Goldilocks zone is not just average temperature, it is about stability. Earth not only has the correct temperature, it has the correct temperature consistently, regulated by natural systems that have worked for eons. It does not require constant human intervention. It does not require massive energy to maintain. It does not require anything to work perfectly all the time. Here is the truth. You must understand. You cannot create a Goldilocks zone artificially. You cannot take a planet that is too hot or too cold and adjust its temperature to something habitable without resources and energy that exceed everything that human civilization can generate. The scales involved are planetary. We are talking about moving entire atmospheres, about altering the radiative balance of entire worlds. Even if we dedicated all of Earth's industrial production exclusively to terraforming Mars for 1,000 years, we would probably achieve nothing more than marginal changes in its habitability. And meanwhile, who would keep civilization on Earth functioning? Who would produce food, maintain infrastructure, tend to the billions of lives that depend on the terrestrial economy continuing? Space colonization is not just technically difficult, it is thermodynamically absurd. It requires us to take worlds in thermal equilibria, fundamentally hostile to life, and force them into new equilibria, fighting the basic laws of physics at every step. And all this, while those worlds do not have any of the natural regulation systems that make Earth maintain its perfect temperature automatically. Imagine existence on a world that is not in the Goldilocks zone. Every moment of your life, depending on heating or cooling systems working perfectly, never a moment of true security. Never a moment where you can simply exist without the constant anxiety that a system failure will kill you in minutes. That is not living. It is precarious survival, and only as long as Earth can continue sending the spare parts and energy that make that survival possible. Contrast that with Earth, where you can walk outside without protection in most places, most of the time, where the temperature is naturally compatible with human life, where even if all technology collapsed tomorrow, humans could survive with primitive tools, because the planet itself is fundamentally hospitable. The Goldilocks zone is not just a region of space, it is an extraordinarily rare condition, a perfect balance of stellar distance, planetary mass, atmospheric composition, and climate regulation systems. It is so rare that in our entire solar system, with its 8 planets and hundreds of moons, it only exists in one place. Here on this planet, in this unique world, where the temperature is perfect, not too hot, not too cold, just at the exact point where life can flourish, without constant heroic effort. And there is nowhere else like it, within light years of distance. Take a deep breath. Feel how the air fills your lungs, how oxygen enters your bloodstream, how every cell in your body receives exactly what it needs to continue living. It is so automatic, so natural, that you never think about it. You inhale, you exhale, over and over again, approximately 20,000 times a day, without conscious effort. But that air you breathe without thinking is an extraordinarily specific mixture, a chemical balance so precise that deviating from it by just a few percentage points would kill you. And that perfect mixture only exists in one known place in the universe. Here, in this thin layer of gases that envelops our planet like an invisible skin. Earth's atmosphere is not just air. It is a precision chemical machine that has taken billions of years to develop, regulated by life itself, in a balance so delicate that trying to replicate it on another world is beyond any technological capability we can imagine. Let us start with the basic composition. Earth's atmosphere is 78.08% nitrogen, 20.95% oxygen, 0.93% argon, and 0.04% carbon dioxide, plus traces of other gases. These numbers are not arbitrary. They are the result of eons of planetary and biological evolution. Nitrogen is inert. It does not react easily. It acts as a diluting gas, preventing oxygen from being so concentrated that everything spontaneously ignites. Yes, you read that correctly. If the atmosphere were 100% oxygen, or even 50%, the world would constantly burn. Every spark would start uncontrollable infernos. Wood, paper, even your clothes would become highly flammable material. Cellulose-rich plants would be essentially bombs waiting to ignite. Oxygen at 21% is the maximum that allows controlled combustion without making everything dangerously flammable. It is enough to sustain complex metabolisms of large animals, but not so much as to turn the world into a fire trap. This balance is critical. But oxygen was not originally in the atmosphere. 3 billion years ago, the Earth's atmosphere had practically no oxygen, primarily nitrogen, carbon dioxide, and methane. Oxygen was produced by cyanobacteria through photosynthesis for billions of years, slowly accumulating until it reached modern levels approximately 500 million years ago. This oxygen is maintained by life. Plants, algae, phytoplankton in the oceans constantly produce oxygen through photosynthesis. Without photosynthetic life, atmospheric oxygen would gradually combine with rocks and disappear over timescales of millions of years. Earth's breathable atmosphere is literally a product of life, maintained by life. Now try to imagine creating this artificially on another planet. Mars has an atmosphere of 95% carbon dioxide, 3% nitrogen, 1.6% argon, with practically no oxygen. And more importantly, the total atmospheric pressure is only 600 pascals compared to 1,300 pascals on Earth. It is less than 1% of our atmospheric pressure. Breathing on the surface of Mars would be like trying to breathe on Earth at an altitude of 35 kilometers, higher than any commercial plane flies. Not only is there not enough oxygen, there is not enough pressure for your lungs to function. Blood would literally boil in your veins due to the low pressure. You would die in seconds. To make Mars breathable, you would need to do two monumental things. Increase the total atmospheric pressure by a factor of 100 and change its composition from almost all carbon dioxide to primarily nitrogen and oxygen. Each of these tasks is individually impossible with conceivable technology. Together, they are absurd. Where would you get enough gas to increase atmospheric pressure 100 times? The total mass of the Earth's atmosphere is approximately 5,000 trillion tons. You would need to add that amount of gas to Mars. It does not exist in any accessible form. The Martian polar caps contain perhaps enough frozen carbon dioxide to double the current atmospheric pressure if you could sublimate it all. That takes you to 2% of the terrestrial pressure, still completely inadequate. Some propose importing comets, balls of ice, and frozen gases, and crashing them into Mars to add atmosphere. Aside from the question of how you deflect objects of billions of tons to collide with a specific planet, you would need thousands of large comets. The energy expenditure of capturing and redirecting so many comets would exceed the total energy production of human civilization for centuries. But let us assume, just for argument, that you magically add enough gas to create terrestrial pressure on Mars. Now, you have a planet with a carbon dioxide atmosphere at breathable pressure. That kills you almost as fast as a vacuum. Carbon dioxide, above a few percent concentration, causes suffocation. At 10%, it causes loss of consciousness in minutes. At 95%, it kills you instantly. You need to convert that carbon dioxide into oxygen. Photosynthesis does this by separating carbon dioxide into carbon and oxygen. But photosynthesis requires life: plants, algae, photosynthetic bacteria. And life requires liquid water, adequate temperatures, nutrients from the soil. We are back to all the problems from previous chapters. Even if you could establish a photosynthetic biosphere on Mars, the process of converting a carbon dioxide atmosphere into a breathable one took Earth billions of years. With massive human effort, perhaps you could accelerate it, perhaps to a few million years or thousands of years in the most optimistically absurd scenario. It is not a timescale on which human civilization operates. And there is another fundamental problem: nitrogen. You need 78% nitrogen in the atmosphere. Mars has very little total nitrogen in its atmosphere, soil, and rocks. There is not enough to create an Earth-like atmosphere, even if you could extract it and release it all. You would need to import nitrogen from somewhere else. Where from? Titan, a moon of Saturn, has a nitrogen-rich atmosphere. It is 1 billion kilometers away. The idea of mining Titan's atmosphere and transporting it to Mars is so absurd that it does not even deserve a detailed calculation of its impossibility. Let us look beyond Mars. Venus has a dense atmosphere 90 times the terrestrial pressure, but it is pure carbon dioxide at 470 degrees Celsius with sulfuric acid rain. Converting that into something breathable would require removing or converting almost all of that massive atmosphere. Some propose seeding Venus with modified bacteria that consume carbon dioxide, but those bacteria would be instantly cooked in the Venusian oven. You would need to cool Venus first, which takes us back to the previous chapter on temperature. The moons of Jupiter and Saturn do not have significant atmospheres at all, just a vacuum or very thin layers of gases. Creating terrestrial atmospheres there would require importing billions of tons of gases. It is literally impossible with any conceivable technology. Here is the cruel truth. You cannot manufacture an atmosphere, not on human timescales, not with available resources. Planetary atmospheres are products of geological and biological processes that operate over eons. They are maintained by delicate equilibria between volcanic emissions, sequestration in rocks, biological production, and escape into space. Earth has maintained a breathable atmosphere for hundreds of millions of years without human intervention. It is self-regulating through biogeochemical cycles. When carbon dioxide levels rise, plants grow faster and absorb it. When they fall too much, respiration and decomposition replace it. The system has stabilizing feedbacks built in through evolution. Trying to create this artificially is like trying to build a human by assembling individual atoms. Technically, all the information is there. We know exactly which atoms go where, but the assembly process is so complex, involves so many simultaneous interactions, that it is completely beyond our capabilities. Only life can create life. Only long-term planetary processes can create truly stable and breathable atmospheres. This means that any human habitat outside of Earth must be completely closed and sealed. You will not breathe the Martian air. You will forever live in pressurized cans, breathing recycled air, depending on machines to remove carbon dioxide and add oxygen. The International Space Station does this. It uses electrolysis to split water into hydrogen and oxygen, providing breathable oxygen. It uses chemical filters to remove carbon dioxide from exhaled air. These systems are complex, require constant maintenance, have components that fail regularly, and must be replaced. A Martian colony would need similar systems, but on an enormously larger scale. For 1,000 people, you would need to generate approximately 450 kilograms of oxygen per day. That requires decomposing approximately 500 kilograms of water daily through electrolysis. The energy required is considerable, and the water consumed must be constantly replenished. And all this assumes nothing fails. A single hole in the habitat and the internal pressure escapes. Without pressure, you die in minutes. Every habitat must be perfectly sealed, constantly monitored, immediately repairable. The constant anxiety that a microscopic meteorite, a defective seal, a failed component, could depressurize your home and kill you. Compare this with Earth, where you simply open a window and fresh air comes in, where you can walk outside without thinking about bringing your own air supply, where the entire planetary atmosphere is your life support system, robust beyond all comprehension, impossible to deplete, automatically regulated. Earth's atmosphere is not just convenient, it is a miracle of chemical complexity, a product of 4.5 billion years of planetary evolution and 3 billion years of biological modification. It is so complex, so finely balanced, that even on Earth, we are discovering that our activities can destabilize it in dangerous ways. And if creating stable atmospheres is impossible outside of Earth, then all space colonization is reduced to living in sealed containers, eternally dependent on technology that cannot fail, connected by invisible umbilical cords to the only source of breathable air in the solar system. This planet, this atmosphere, this perfect mixture of gases that we take for granted with every breath. There is no atmospheric plan B. There is no way to make other worlds breathable on timescales that matter. There is only the option of living in artificial bubbles, fragile shelters on hostile worlds, or staying here, where the air you need to live simply exists, abundant and free. A gift from a planet that spent eons preparing to sustain you. Stand up. Feel the weight of your body pressing down, your legs supporting you without conscious effort, your bones resisting compression, your muscles automatically adjusting to keep you upright. It is so natural that you never think about it. Your heart pumps blood against gravity to your brain. Your inner ears detect which direction is up. Your muscles have been calibrated to lift objects, to walk, to move in this specific environment. Now imagine that all that calibration, those 4 billion years of evolution that shaped every system in your body, suddenly become incorrect. That the gravity that defined how your bones formed, how your heart pumps, how every organ works, simply changes. It is not that you gradually adapt. It is that your body begins to fail immediately, because it is designed down to the molecular level for an environment that no longer exists. This is what happens when you leave Earth. Your body was not made for space. It was made for here, only for here, and changing that is impossible. Let us start with the most obvious: bones. Your skeleton is not a static structure. It is living tissue that is constantly remodeling itself. Cells called osteoblasts build new bone. Cells called osteoclasts break down old bone. This process is in dynamic equilibrium, regulated by the mechanical forces you experience. When you load weight onto your bones, when you walk, run, simply stand, the osteoblasts receive signals that bone is needed and must be maintained or strengthened. Without that load, without that constant tension of terrestrial gravity, The osteoclasts continue to break down bone, but the osteoblasts slow down their building. The result is progressive bone loss. Astronauts on the International Space Station lose approximately 1 to 2% of their bone mass per month. It does not sound like much until you do the math. After 6 months, they have lost between 6 and 12% of their bone density. After 1 year, between 12 and 24%. That is the equivalent of decades of osteoporosis, compressed into months. The most affected bones are those that bear weight on Earth. The spine, pelvis, femurs, exactly the bones you need to walk and support your own weight when you return to gravity. Astronauts who spend long periods in space return with the fragile bones of the elderly, even if they are 20 or 30 years old. Some studies suggest that part of this bone loss is never fully recovered. Now imagine a Martian colony. Mars has 38% of Earth's gravity. It is more than zero gravity, but it is not enough. Models suggest that Martian colonists would experience continuous bone loss, perhaps slower than in zero gravity, but continuous. After years, their skeletons would be so weakened that returning to terrestrial gravity would be impossible. Their bones would simply break under their own weight. This means that going to Mars is a one-way trip, not by choice, but by biology. Your body would adapt to the low gravity, becoming incompatible with Earth. You would be permanently exiled, not by politics, but by physiology. But bones are only the beginning. Your muscles also atrophy in low gravity. You do not need strong leg muscles to move in zero or low gravity, so your body, ever efficient, breaks them down. Astronauts lose up to 20% of muscle mass over prolonged periods in space, despite exercising 2 hours a day. Your heart is a muscle. In terrestrial gravity, it has to work constantly to pump blood from your legs to your head against gravity. In microgravity, that work disappears. The heart weakens, becomes smaller, less efficient. Ultrasound studies show that astronauts' hearts become more spherical, losing their efficient shape. When they return to gravity, their weakened hearts struggle to do the work they used to do effortlessly. The entire circulatory system changes. On Earth, gravity causes blood to pool in your legs. Your body compensates for this. In zero gravity, blood redistributes towards the head and chest. Your face swells, your legs thin. Your body detects the excess fluid in the upper part and tries to correct it by producing less blood. Astronauts lose up to 22% of their blood volume in space. Less blood means less oxygen carrying capacity. It means lower physical endurance. It means that when you return to gravity and suddenly need that blood volume, so you do not get dizzy every time you stand up. Your body does not have it. Astronauts frequently experience severe dizziness and fainting upon returning to Earth. Then there is the immune system. Multiple studies show that immune function is suppressed in space. White blood cells do not work as effectively. Astronauts are more susceptible to infections. Latent viruses in their bodies, like herpes, reactivate more frequently. A minor infection that your body would normally fight easily on Earth can become serious in space. Why does this happen? No one knows completely, but it seems that the immune system evolved to function under terrestrial gravity. Change that, and it stops working optimally. It is another system calibrated for Earth that fails when you leave it. The vestibular system, your sense of balance, is completely dependent on gravity. Small structures in your inner ears, called otoliths, detect which direction is down by means of crystals that fall on sensitive hair cells. In zero gravity, they do not fall in any direction. Your sense of balance becomes useless. Approximately 70% of astronauts experience severe nausea and disorientation when they first arrive in space, a syndrome called space adaptation. Eventually, you adapt. Your brain learns to ignore the conflicting signals from your inner ears. But then, when you return to gravity, you have to adapt again. And if you spend years in Martian gravity, your vestibular system would calibrate for that gravity. Returning to Earth would make you feel like you are in a centrifuge, with everything weighing 2.6 times more than your body now expects. Vision is also affected. Many astronauts develop vision problems in space. The fluid that redistributes towards the head increases intracranial pressure. This can flatten the back of the eyeball, change the shape of the optic nerve, cause swelling. Some astronauts have experienced permanent changes in vision after long missions. No one knows if this damage is progressive or if it could lead to eventual blindness in prolonged exposure. At the cellular level, microgravity affects how cells divide, how proteins fold, how basic metabolic processes work. Studies show that gene expression changes in space. Thousands of genes are activated or deactivated differently than on Earth. This affects everything: how cells repair themselves, how they respond to stress, how they age. There is evidence that astronauts age faster in space. Their telomeres, the protective caps on the ends of chromosomes that shorten with age, show abnormal patterns. Their risk of cancer increases not only due to radiation, but also because DNA repair mechanisms do not work as well. Then, there is the brain. Recent magnetic resonance imaging studies show that astronauts' brains physically change in space. Cerebrospinal fluid redistributes. The brain shifts slightly upwards in the skull. Some studies suggest changes in gray matter. We do not know the long-term consequences because no one has spent more than one consecutive year in space. Cosmic radiation, as we discussed in a previous chapter, damages neurons. Unlike other cells, neurons are not replaced. The damage is permanent. Astronauts on long trips to deep space could return with irreversible cognitive decline, memory problems, personality changes. And here is the most terrifying question: what happens to human development in low or zero gravity? We have never attempted to conceive, gestate, or raise a child in space. We do not know if human fertility works normally in low gravity. We do not know if embryos develop normally. We do not know if babies can form adequate bones and muscles without terrestrial gravity. Experiments with animals are concerning. Mice gestated in space show developmental problems. Their vestibular systems do not form correctly. Their bones and muscles are abnormal. Some studies suggest that without gravity, normal development might be impossible. If this is true for humans, it means that space colonies could not be self-sustaining. Each new generation would have to be conceived and gestated on Earth, then sent into space. You cannot call that colonization. It is barely temporary occupation, eternally dependent on Earth to provide new inhabitants. Even if fetal development works in low gravity, children raised on Mars could never visit Earth. Their bodies, formed under 38% of terrestrial gravity, could not withstand full gravity. They would be prisoners of Mars from birth, physically incapable of experiencing the world their parents left behind. This creates a permanent division in humanity. Terrans adapted to full gravity, Martians adapted to partial gravity, permanently exiled. Lunarians, if they existed, would be even more fragile, with only 16% of terrestrial gravity. They would not be different races by genetics, but by physiological adaptation to the environment. And they could never mix, because their bodies require different gravities to function. Some propose technological solutions, rotating habitats that create artificial gravity through centrifugal force. It sounds smart until you consider the scale. To comfortably simulate terrestrial gravity, you need a structure of at least several hundred meters in diameter, rotating at a considerable speed. The engineering involved is immense. The energy expenditure of maintaining constant rotation is significant, and any failure in the rotation system would be catastrophic. More fundamentally, rotating habitats do not help when you go outside. On the surface of Mars or the Moon, you experience the local gravity. Every activity outside the habitat exposes your body to incorrect gravity. Your vestibular system is constantly confused, alternating between artificial gravity inside and real gravity outside. Dizziness and disorientation would be perpetual. The uncomfortable truth is that evolution chained us to this planet. Every system in your body was optimized over millions of years to function exactly under 9.8 meters per second squared of gravitational acceleration, at the exact atmospheric pressure of Earth, in the exact air composition, at the exact temperatures. You are not a generic human design that can function in any environment with some technological modifications. You are an organism of Earth, as specialized for this planet, as a fish is for water. Take a fish out of water, and it dies. Take a human out of Earth, and they start to deteriorate immediately. You could argue that technology can compensate. Suits that simulate gravity through compression, medications that prevent bone loss, gene therapy that modifies how cells respond. But every intervention is a patch on systems that are fundamentally out of their designed environment. Each patch requires constant maintenance, introduces new risks, can have unknown side effects, and you can never fully replicate the terrestrial environment, because that environment is the entire planet. It is the gravity generated by a sphere of rock the size of Earth. It is the atmosphere that has been present throughout the evolution of terrestrial life. It is the magnetic field, the temperature, the 24-hour day-night cycle, the seasons, everything. Your circadian rhythm is calibrated for a 24-hour day. Mars has days of 24 hours and 40 minutes. It sounds like a trivial difference, but studies show that even small misalignments of the circadian rhythm cause cumulative health problems. Sleep disorders, metabolic problems, increased risk of diseases. Your skin evolved with a certain amount of UV exposure from the sun, filtered by the Earth's atmosphere. Too little, as in windowless artificial habitats, and you develop vitamin D deficiencies, depression, weakened immune systems. Too much, as under the Martian sun, without adequate atmospheric filtering, and skin cancer rates would skyrocket. Your microbiome, the trillions of bacteria that live in and on your body, evolved with humans on Earth. These microbes are essential for digestion, immune function, even mental health. How they behave in space environments is largely unknown. Some studies suggest that bacteria become more virulent in space. Others show that the composition of the microbiome changes in potentially harmful ways. Every aspect of your physiology is a reminder that you are a product of this planet. Not a temporary visitor, not an explorer who can go anywhere, but a native of Earth, shaped by it, dependent on it, incapable of truly functioning anywhere else. You can survive in space, temporarily, with massive technological support. You can exist in artificial bubbles that attempt to simulate aspects of the terrestrial environment, but you will never be healthy. You will never be fully functional. You will never be truly home. You will always be slowly deteriorating, your body confused by wrong environmental signals, fighting adaptations that make you less capable of surviving in any gravity. Earth is not just where we evolved. It is part of who we are. It is written in our DNA, encoded in every cell, inseparable from our basic biology, and you cannot rewrite 4 billion years of evolution with technology or willpower. There is one number that shatters all fantasies of space colonization. A number so brutal, so relentless, that no amount of technological optimism can overcome it. That number is $3 billion per person per year. That is approximately what it costs to maintain astronauts on the International Space Station. The annual operating budget of the station is approximately $3 billion, maintaining an average crew of 6 people. That is $500 million per astronaut per year. And that is in low Earth orbit, just 400 kilometers away, where supplies can arrive in a few hours. To put this in perspective, with $500 million annually, you could provide basic food, clean water, shelter, medical care, and education to approximately 250,000 people in developing countries. The cost of maintaining one human in space is equivalent to keeping 250,000 people alive on Earth. This is not an ideological comparison about how we should spend the money. It is a demonstration of the fundamental economics of space. It is absurdly, prohibitively, impossibly expensive to sustain human life outside of Earth. And this brutal economy will never improve enough to make mass colonization viable. Let us start by breaking down where these costs come from. It is not that NASA is inefficient or that we are using outdated technology. It is that space is inherently hostile, and everything you need to survive must be sent from Earth or manufactured with resources that were sent from Earth. Food. A human needs approximately 2 kilograms of food per day. That is 730 kilograms per year. Currently, launching 1 kilogram to the International Space Station costs approximately $10,000 using the cheapest rockets available. That is $14.6 million. Just in launch costs to feed one person for 1 year. And that is only to get the food there, not counting the cost of producing specialized space food, packaging it, storing it. Water, although recycled on the station, there are continuous losses. You need to replenish approximately 50 kilograms of water per person per year, even with 90% recycling. That is another $1 million in launch costs. Oxygen, currently generated through electrolysis of water, but the equipment requires maintenance, spare parts, eventual replacement. Amortized, perhaps another couple of $1 million per person per year. But these consumables are only a fraction of the real cost. The majority of the expense is infrastructure, maintenance, and support personnel on the ground. The International Space Station requires 24-hour mission control teams, engineers constantly analyzing telemetry data, specialists planning every activity. Ground support personnel far outnumber the astronauts in orbit. For every person in space, there are hundreds on Earth, making their survival possible. Equipment in space constantly breaks down. Radiation degrades electronics, seals deteriorate, batteries wear out. Life support systems require continuous maintenance. Spare parts must be launched regularly. Every component that fails must be replaced, often requiring complex spacewalks that entail their own risks and costs. Now let us consider what this would mean for a Martian base. Mars is 1,000 times farther away than the International Space Station. Launch windows only occur every 26 months, when the planets are aligned correctly. Travel time is 9 months in each direction. You cannot simply send an urgent spare part if something critical fails. You have to wait more than 2 years in the worst case. This means that a Martian base needs massive redundancy, multiple copies of every critical system, enormous warehouses of spare parts for anything that could fail. All of this must be sent in advance, multiplying launch costs. And remember, launching to Mars requires much more energy than launching to low Earth orbit. The costs per kilogram would probably be 10 times greater, perhaps $100,000 per kilogram with current technology. That makes feeding one person on Mars cost $146 million a year, just in launch costs for food. Some argue that you will grow food locally in Martian greenhouses, reducing dependence on shipments from Earth. This sounds reasonable until you consider what it takes to build and operate those greenhouses. A greenhouse requires airtight and pressurized structures, transparent to let light through, but strong enough to contain an atmosphere against the Martian vacuum. It requires soil, which Mars does not have, only toxic regolith, full of perchlorates. You need to import or manufacture real soil with nutrients, microorganisms, organic structure. It requires water, which, as we discussed, must be mined, melted, and purified. It requires heating, because Martian nights are 80 degrees below zero. It requires supplementary lighting, because Mars receives only 43% of the sunlight that Earth does. It requires radiation protection that would destroy exposed plants. It requires pollination systems, because there are no insects on Mars. Each of these requirements implies equipment that must be sent from Earth, energy that must be generated, maintenance that must be performed. The cost of building sufficient agricultural capacity to feed even a dozen people would probably be in the billions of dollars, and the system would still depend on continuous support from Earth. Energy is another massive cost. On Earth, Energy is relatively cheap because we have fossil fuels accumulated over millions of years, hydroelectricity from natural water cycles, wind from atmospheric temperature differences. On Mars, you have solar panels or nuclear reactors. Solar panels on Mars are less efficient because there is less sunlight, and dust storms regularly cover them, reducing production by up to 90% for weeks. You would need vast expanses of panels with automated cleaning systems, all sent from Earth at astronomical costs. Nuclear reactors are more reliable, but they require refined nuclear fuel, shipped from Earth under strict safety regulations, multiplying costs. They require specialized maintenance, produce radioactive waste that must be managed somehow, and eventually run out, needing complete replacement. A Martian base of only 100 people would probably require tens of megawatts of reliable electrical generation. The infrastructure to provide this would cost billions just to build and hundreds of millions annually to maintain and resupply. Now, let us multiply these costs by a significant population. For something to qualify as a real colony, rather than a research station, you need at least thousands of people. Let us say 10,000, the size of a small city. The annual costs would be literally trillions of dollars. Trillions of dollars, annually in perpetuity, to keep 10,000 people surviving in a radioactive frozen desert, where every breath depends on machines. The total gross domestic product of the United States is approximately $23 trillion. Maintaining a Martian colony of 10,000 people could easily consume 10% of that each year, producing no economic return, because there is nothing on Mars worth bringing back that justifies the transportation costs. This leads us to the fundamental economic question: what value will a Martian colony produce to justify these costs? What will a Martian colony produce that has sufficient value to justify these costs? In Earth's history, colonies were economically viable because they produced valuable resources: spices, gold, crops, eventually manufactured goods. These resources could be sent back and sold for profits that exceeded the costs of maintaining the colony. What does Mars have that Earth wants? Practically nothing. Any mineral or element that exists on Mars also exists on Earth in much more accessible forms. There are no unique resources that justify the costs of interplanetary transport. Some suggest that Martian colonies will produce valuable scientific knowledge, but science does not generate direct economic returns on scales that matter here. You can justify a small research station with that argument, how we justify bases in Antarctica. You cannot justify cities of millions of people. Others argue about asteroid mining or manufacturing in microgravity. But these activities do not require colonies on Mars. If anything, Mars is poorly located for them. Asteroids are closer to Earth than Mars on average. Manufacturing in microgravity would be better done in Earth orbit, where access is easier. The brutal reality is that Martian colonies would be pure economic drains, consuming vast resources without producing returns. They would only be sustainable as long as terrestrial civilization is willing and able to subsidize them indefinitely. And here is the existential risk. Space colonies depend completely on the terrestrial economy, remaining robust and stable. Any major disruption on Earth, a serious economic recession, a war, a collapse of civilization, and the supply lines to the colonies are cut. Without continuous supplies from Earth, the colonies collapse in weeks or months, as critical systems fail without spare parts. This means that space colonization does not make humanity more resilient, it makes it more fragile. It creates populations that cannot survive without constant support from Earth, while draining resources that could make terrestrial civilization more robust and capable of handling crises. Compare the costs of space with what those same resources would achieve on Earth. The billions spent annually on space operations could build thousands of schools and hospitals, develop sustainable agriculture, feeding millions, research, renewable energy, accelerating the transition from fossil fuels, protect ecosystems and biodiversity, improve water infrastructure, bringing clean water to every human being, research medicine, curing diseases, literally saving millions of lives annually, versus keeping a handful of people surviving on Mars in perpetual dependence on Earth. This is not a question of whether we should explore space. Robotic exploration, telescopes, scientific probes provide immense knowledge at fractions of the cost of crewed missions. It is a question of whether it makes sense to try to establish permanent human populations, where the costs are orders of magnitude greater than any conceivable benefit. Space enthusiasts talk about making space economically viable through technological advances. SpaceX has significantly reduced launch costs with reusable rockets. But even if launch costs fell by a factor of 10, which would be extraordinary, maintaining someone on Mars would still cost millions of dollars annually. It would still be absurdly expensive, and there are fundamental physical limits to how low costs can drop. Remember Chapter 1 about gravity. It requires fixed amounts of energy to escape the terrestrial gravitational well. You cannot negotiate with physics, even with perfectly efficient technology. Pure energy costs provide a lower limit. The sad truth is that the economics of space will never work for mass colonization. The costs are too high, the returns non-existent, the dependence on Earth absolute. You can maintain small research stations, the way we maintain bases in Antarctica, as subsidized scientific ventures, but cities, nations, real civilizations, the mathematics simply do not work. And so, we face the central paradox of space colonization. It can only sustain populations in space as long as terrestrial civilization is prosperous and stable. But if terrestrial civilization is prosperous and stable, why dedicate massive resources to maintaining populations in mortally hostile environments instead of investing in making Earth even more habitable and civilization more resilient? The only justification would be if Earth faced an imminent existential threat that space could avoid. But almost any catastrophe you imagine, nuclear war, asteroid impact, climate collapse, is easier to survive in the midst of it on Earth than on pristine Mars. Even an Earth devastated by nuclear war would be more hospitable than pristine Mars because it would still have breathable air, accessible water, correct gravity, and magnetic protection. The numbers do not lie. The economics of space are brutal, relentless, and immutable, and they tell us that space colonies will remain expensive fantasies, not because we lack will or vision, but because physics, biology, and economics combine to make human survival outside of Earth prohibitively expensive and dependent on terrestrial supply lines that can never be broken. The illusion of colonization. There is a word we constantly use when we talk about space. A word that evokes images of pioneers taming new lands, of self-sufficient communities flourishing on distant frontiers, of civilizations expanding beyond their origins. That word is colonization, and it is deeply misleading. When you look closely at what proposals for space colonies actually mean, you discover something very different from what that word implies. They are not colonies at all. They are dependent life support stations, connected by invisible, yet absolutely essential, umbilical cords to the only source of everything they need to exist, Earth. To understand why, we need to examine what colony truly means versus what outpost or station means. In human history, colonies were settlements that eventually became self-sufficient or even surpassed their places of origin. European colonies in the Americas imported supplies and people initially, but quickly established agriculture, built industries, and extracted local resources. Within generations, they were economically independent. Within centuries, some became world powers that eclipsed their founders. This was possible because the settlers arrived in fundamentally habitable environments. There was breathable air, abundant fresh water, fertile soil, fauna, and flora that could be hunted or domesticated, climates where humans could survive without complex technology. Yes, colonization was difficult and often brutal, but the Earth itself provided the basic elements of survival. Outposts are different. Research bases in Antarctica are outposts, not colonies. They exist only with constant resupply from the outside. If ships and planes stopped arriving, they would be abandoned in months. They are not self-sufficient. They do not reproduce. They do not grow organically. They are temporary occupations of hostile environments, possible only with continuous supply lines. Every proposed space colony is really a glorified outpost. And the difference is not semantic, it is fundamental. Let us consider what real self-sufficiency requires. A self-sufficient community must be able to produce all its own food, not just grow vegetables in subsidized greenhouses with imported nutrients, but complete agricultural cycles, including grains, proteins, fats, vitamins, raising livestock or equivalents, managing complete ecosystems where the waste from one process feeds another, manufacture all the necessary tools and technologies for its survival. This means not just small workshops, but complete industrial chains, mining of raw materials, refining into metals and chemicals, manufacturing of electronics, plastics, textiles, and construction materials. When something breaks, it must be repairable or replaceable locally. Generate all its energy from local, renewable, or long-term sources. It cannot depend on shipments of fuel or critical components from outside. Maintain its population through natural reproduction. Children must be able to be born, develop healthily, and eventually contribute to the community without importing new individuals. Handle all medical emergencies with local resources. Complete hospitals, not just basic clinics, surgical capacity, pharmaceutical production. Now, let us apply these criteria to a hypothetical Martian base. Food. As we discussed, Martian greenhouses require imported structures, manufactured or imported soil, water mined with imported equipment, energy generated with imported equipment. Every component of the agricultural system depends on Earth. When a seal fails, when a pump breaks, when the water filtration system stops working, you need spare parts from Earth. It is not self-sufficiency, it is externally subsidized agriculture or industry. This is where the colonization argument completely collapses. The modern industrial supply chain is incredibly complex. Consider something as simple as a screw. It requires extraction of iron ore, smelting into steel, wire formation, thread cutting, heat treatment. Each step requires specialized machinery. Now consider something complex like a computer. It requires dozens of different materials. Ultra-pure silicon for chips, rare earth metals for electronic components, precise plastics for casings, metals for connections. Each material requires specialized refining processes. Silicon for chips must be purified to 1 part in a billion of impurities, something that requires massive industrial facilities. Chip manufacturing itself requires clean rooms, where the air is millions of times cleaner than a normal environment. Lithography machines that cost hundreds of millions of dollars each. Ultra-pure chemicals, the processes of 1,000 steps each. Crucially, a single semiconductor factory on Earth costs tens of billions of dollars to build and requires a whole network of suppliers, providing thousands of specialized components and chemicals. You cannot replicate this on Mars with a population of hundreds or even thousands. It requires economies of scale, of millions, industrial infrastructure built over generations, global networks of specialized trade. Without the capacity to manufacture electronics, your Martian base depends completely on every chip, sensor, processor, and cable being sent from Earth. And electronics fail. Radiation degrades them faster on Mars than on Earth. Without constant replacements, your systems collapse. The same applies to literally everything. Mechanical, spare parts, batteries, solar panels that degrade over time, medications that expire, spacesuits that wear out, tools that break. Everything must be resupplied from Earth, because building the industrial infrastructure to make them locally is orders of magnitude beyond what a small population can achieve. Some proposals talk about using three-dimensional printing and additive manufacturing to produce things locally. But three-dimensional printers do not create materials out of thin air. They need specific raw materials: metal powders, plastics, resins. These must be refined from Martian raw materials or imported. And three-dimensional printers themselves are complex devices with electronics, precision motors, components that fail. You need three-dimensional printers to manufacture parts for three-dimensional printers, which requires industrial capabilities that bring us back to the same problem: population. We do not even know if human reproduction works normally in Martian gravity. Assuming it does, raising children on Mars presents monumental challenges. They need education, but from whom? A small population cannot support complete specialization. You cannot have dedicated teachers, doctors, engineers, scientists, technicians, farmers, all in a community of hundreds. On Earth, civilization works because we have billions of people allowing extreme specialization. You can spend decades becoming an expert neurosurgeon because thousands of other people grow your food, build your shelter, maintain infrastructure, manufacture tools. A Martian base of 1,000 people cannot support this level of specialization. Everyone must be a generalist, which means no one is truly expert in the complex things needed to keep the technology functioning. Medicine. A serious medical emergency on Mars is a death sentence. There are no air ambulances that can take you to a trauma center in minutes. There are no specialists in every medical field available. There are no pharmaceutical supply chains producing thousands of different drugs. Appendicitis, routinely treatable on Earth, could be fatal on Mars if the base's general practitioner is not trained in surgery or if the correct antibiotics are not in stock. The standard argument is that eventually, with enough time and resources, Martian bases will develop all these capabilities and become truly self-sufficient. But this argument ignores the scales involved. It took humanity 10,000 years to go from small agricultural communities to complex industrial civilization on Earth, and that was with an entire planet of accessible resources, a benign climate, and natural ecosystems providing free services. Mars offers none of these advantages. Building complete industrial capacity on Mars would essentially require recreating the entire industrial revolution in an environment 1,000 times more hostile. You would first need to establish mining, extracting all the necessary elements, then refining, converting minerals into usable materials, then basic manufacturing, creating simple tools, then advanced manufacturing, creating complex machines, then precision manufacturing, creating sophisticated electronics and components. Each step requires the previous one to be functioning. You cannot skip steps. You cannot manufacture chips without first having the capacity to produce ultra-pure silicon, which requires massive energy, which requires energy infrastructure, which requires advanced manufacturing. It is circular. Breaking the circle requires importing enormous amounts of equipment and capacity from Earth. And throughout this development, which would probably take centuries, even in the best-case scenarios, the base remains completely dependent on Earth for basic survival. If shipments from Earth stop at any point during this development, the base collapses. There is no real independence until the entire industrial chain is complete and functioning. Consider analogous historical scenarios. When European colonies were established in the Americas, they brought knowledge, basic tools, and seeds, but they found entire continents of accessible resources, breathable air, functional ecosystems. Even so, it took generations to achieve even basic self-sufficiency. Imagine if those settlers had arrived on a continent where the air was poison, where every drop of water had to be extracted from frozen rock, where every moment outside sealed shelters meant death in seconds, where every tool that broke was irreplaceable. Colonization would have been impossible. The Americas would never have been settled. The outposts would have been abandoned after the supply ships stopped arriving. That is Mars. That is every location in the solar system except Earth. Advocates of space colonization often invoke a pioneer spirit. They talk about how humans have always explored, always overcome obstacles. But this confuses exploration with colonization and technical possibility with practical viability. Yes, we can send people to Mars. It is technically possible. Yes, we can keep them alive there for extended periods with enough investment. But this is no different from keeping people alive on the summit of Mount Everest or at the bottom of the ocean. Technically possible, but no one calls this colonization because everyone understands that it requires constant support from outside. The difference with space is that it is far away, which makes it dramatic and romantic. But distance does not change the fundamental dependence. It only makes the supply lines longer, more expensive, more fragile. Here is the hardest truth. Calling these space bases colonies is not just inaccurate. It is dangerous because it creates wrong expectations. It makes people think we are building independent civilizations that can survive even if Earth faces catastrophe. It makes it seem like we are making humanity multiplanetary, distributing risk. But we are not. We are creating costly outposts that are absolutely dependent on terrestrial civilization remaining robust. If Earth faces a serious catastrophe that interrupts its capacity to launch supplies, the Martian colonies die with it. We do not distribute risk, we concentrate it, because we drain resources from Earth that could be used to make it more resilient. The great illusion of space colonization is that we can create miniature versions of terrestrial civilization on other worlds that will sustain themselves. But civilization does not scale downward in that way. It requires a critical mass of population, resources, and infrastructure that only exists on Earth. Perhaps, in some distant future, if humanity expands to billions in space over millennia, the economy of scale will make true self-sufficiency possible. But that future requires us to get there, which requires Earth to remain habitable and prosperous for that entire millennium of development. And if we can do that, then we have already solved the long-term sustainability problem, making space colonization for survival unnecessary. Space bases have value for scientific research, for inspiration, perhaps eventually for very specialized industries like the manufacturing of exotic materials or space tourism for the ultra-rich. But they are not colonies. They are not backups for humanity. They do not make us a multiplanetary species in any meaningful sense. They are outposts, as dependent on Earth as an astronaut is on their spacesuit. You can call them colonies, you can dream of Martian cities, but dreams do not change the physics, the biology, or the economics that make true independence impossible on any timescale that matters for current civilization. The liberating truth: Earth is our only home. After everything we have explored, after examining every barrier that ties us to this planet, we might feel disillusioned. The bright promises of Martian cities, of humanity expanding among the stars, of becoming a multiplanetary species, all are revealed as beautiful, yet unattainable fantasies. It might seem like we have lost something precious, some inspiring vision of our future. But here is the truth you need to understand. We have lost nothing. We have gained something much more valuable. We have gained clarity. We have gained appreciation. We have gained the profound understanding of how extraordinary, how improbable, how precious is the world we already have. For decades, the narrative of space colonization has served a peculiar purpose in our culture. It has allowed us to avoid confronting uncomfortable truths about our only home. When we talk about saving humanity by establishing colonies on Mars, we are implicitly saying that Earth is dispensable, that if we ruin it, we have backup options. This mentality is dangerous, precisely because it is false. We do not have backup options. There is no planet B. There is no refuge if Earth becomes uninhabitable. The mathematics are clear. The physics is relentless. The biology is inflexible. We are terrestrial creatures, so fundamentally tied to this planet as trees are tied to the soil. We can survive briefly outside our natural habitat, with massive technological support, just as a human can survive underwater in a diving suit. But that does not make us an aquatic species, and space stations do not make us a space species. This understanding should not lead us to despair. It should lead us to something much deeper: absolute gratitude and the urgency to protect what we have. Think about what it truly means that Earth is our only possible home. It means that this planet is not a prison from which we must escape. It is a sanctuary, the only known place in the universe, perfectly calibrated for our survival. Every feature we have examined, every supposed barrier to space colonization, is actually a reminder of why Earth is miraculous. The gravity that keeps us tethered here also sustains our atmosphere, allows water to flow, and makes complex life possible. The magnetic field, which does not exist anywhere else nearby, protects us from deadly radiation every second of every day without us noticing. Liquid water, which is almost impossible to find elsewhere, covers 70% of our surface, free, abundant, constantly renewed by cycles that work automatically. The perfect temperature that is so rare in the cosmos is maintained by natural climate regulation systems that operated for millions of years before humans existed. The breathable atmosphere that we cannot replicate was created by life itself over eons, a process so complex that we are just beginning to understand it. And our own bodies were shaped by evolution over 4 billion years specifically for this world. Every cell calibrated for this gravity. Every system optimized for this atmosphere. Every organ designed for these cycles, these temperatures, this environment. We are not temporary visitors on Earth. We are products of it, inseparable from it, literally made of its atoms and molded by its conditions. The brutal economics of space tell us that we will never have the resources to move significant civilization beyond this planet. But this is not a limitation. It is a recognition that civilization itself is a product of terrestrial abundance. Free air, free water, solar energy converted into food by free plants, ecosystems that recycle waste and renew resources without human intervention. Trying to replicate this artificially on dead worlds would require resources that simply do not exist. The space colonies we so imagine will always be outposts, fragile, eternally dependent on the only place where life flourishes without constant heroic effort. There is no escape from Earth because there is nowhere else to go, where we can be what we are. Complex, fragile, extraordinarily specialized beings for conditions that only exist here. And this is perfectly fine. More than fine, it is liberating. Because once you accept that Earth is all we have, that it is all we will ever have, that there is no plan B or backup world waiting to save us from our mistakes, then the priority becomes crystal clear. We must protect this planet with everything we have, not as a moral preference or a political stance, but as an absolute survival imperative. Every forest we destroy, we are destroying part of the life support system upon which we are absolutely dependent. Every species we drive to extinction, we are unraveling the web of life that sustains us. Every degree we warm the climate, we are destabilizing the regulation systems that have kept Earth habitable for millions of years. We cannot simply move to another planet when this one becomes too damaged. This is the only planet that can sustain us. The resources we would spend trying to make Mars marginally less deadly should be spent making Earth more resilient, more sustainable, more capable of supporting human civilization for millennia to come. The technology we would develop to survive in the frozen deserts of other worlds should be applied to restoring the deserts of our own world, to cleaning our oceans, to stabilizing our climate. The human ingenuity that would dream of cities under Martian domes should focus on sustainable terrestrial cities that work with natural ecosystems instead of against them. The energy that would be required to make another planet temporarily habitable should be dedicated to keeping this planet permanently habitable. This does not mean abandoning space exploration. Telescopes teach us about the universe, Robotic probes explore other worlds at fractions of the cost of crewed missions. Satellites help us understand and protect Earth. Research in space stations provides valuable knowledge. These activities make sense. What does not make sense is the fantasy of mass colonization, the dream of moving significant human civilization beyond the only world where it can exist. There is profound beauty in accepting our place in the cosmos. We are not destined to spread life across the galaxy. We are custodians of an extraordinary experiment that happened on a particular planet under extraordinarily improbable conditions. For 4.5 billion years, Earth has been refined into a machine for creating and sustaining life. It is the only place within light years where chemical complexity reached the point where molecules became conscious of themselves. You are a product of that process. Every atom in your body was formed in stars that died billions of years ago. Those atoms traveled through space, condensed on this planet, were incorporated into simple life, evolved for eons, and eventually combined into the specific configuration that is you. You are literally stardust, organized in ways that allow you to contemplate stars. But this organization, this extraordinary complexity that allows you to think, feel, dream, is only possible here. Dismantle this perfect machine called Earth, and complexity collapses. Life is reduced to basic survival in sealed bubbles. Consciousness is consumed by constant anxiety about systems that cannot fail. Civilization contracts to dependent outposts, not glorious expansion. The universe is vast beyond comprehension. There are probably billions of planets in our galaxy. Some may harbor life, but they are so unbelievably far away that we will never reach them. The distances between stars are not technological barriers that we will eventually overcome. They are fundamental physical abysses that define the limits of the possible. The closest star, Proxima Centauri, is 4.2 light-years away. That is 40 trillion kilometers. Our fastest spacecraft would travel for 70,000 years to get there. Even if we could build ships that traveled at 10% of the speed of light, something completely outside of current or foreseeable technological capacity, it would take 42 years to reach the nearest star system, and we do not know if there are habitable planets there. Cosmological distances are not just large, they are so absurdly vast that they make interstellar travel an even greater fantasy than Martian colonization. The galaxy is our prison, not for lack of technology, but for fundamental laws of physics that limit how fast information or matter can travel. We are alone, not in the sense that there is no other life in the universe. There probably is, but in the sense that we are isolated, confined to this solar system, this planet, by barriers that no amount of technological progress will overcome. Earth is our only option, not for centuries, but probably for the entire duration of the human species. And that is fine, because Earth is sufficient. It is more than sufficient. It is everything we need. Think of the extraordinary diversity of experiences possible only on this planet. Oceans that cover entire worlds of life, mountains that rise kilometers into the sky, deserts, jungles, Arctic tundras, coral reefs, prairies, forests of every imaginable type, human cultures so diverse that a single lifetime is not enough to experience them all. Art, music, literature, philosophy, science, all the richness of human experience, accessible without leaving this world. Most humans will never experience all the diversity that Earth offers. Why dream of monotonous Martian deserts when we have not fully explored terrestrial deserts? Why long for sealed domes on the moon when we have not fully appreciated the wonders of the world we have? The fascination with space colonization often comes from dissatisfaction with Earth, a feeling that we are finished with this planet and need new frontiers. But this is an illusion born of not truly appreciating what we have. Earth is not small. It contains effectively infinite spaces of human experience. It is not limited in any sense that matters for the time that human civilization will exist. The problems we face, climate change, biodiversity loss, environmental degradation, are not reasons to abandon Earth. They are urgent calls to protect it better because there is nowhere else to go. There is no evacuation plan. There is no new planet waiting to be terraformed. There is only this one, this unique blue world, this extraordinary convergence of conditions that makes everything we are possible. When you look at Earth from space, as astronauts have done, what you see is a delicate sphere floating in infinite darkness. Carl Sagan called it a pale blue dot. That small dot is everything. Every person you have loved, every human achievement, every work of art, every thought ever thought, all happened here, on this speck of dust, suspended in a sunbeam. That perspective should not make us feel insignificant. It should make us feel responsible. We are the guardians of something extraordinary, something that might be unique in the observable universe. And our job is not to escape from it. It is to preserve it, understand it, appreciate it, pass it on to future generations in the same or better condition than we found it. The idea that we will abandon Earth is comforting precisely because it is false. It allows us to imagine that our actions here do not have ultimate consequences, that if we mess up this planet, we can simply move to the next one. But the inconvenient, uncomfortable, absolutely essential truth is that we cannot. This is our only home. It always has been, it always will be. And once you truly accept that, not as an admission of defeat, but as a recognition of reality, something changes. The urgency to protect this planet becomes visceral. The madness of destroying ecosystems, of destabilizing the climate, of extinguishing species, becomes unmistakable. Because we are not damaging the environment as something separate from us. We are damaging the only life support system that exists for us in the entire known cosmos. We are Terrans. That is what we are. Not aspiring Martians, not future galactic colonizers, but Terrans, products of this planet, sustained by it, incapable of truly existing anywhere else. And there is deep dignity in accepting that, in being who we are, instead of fantasizing about becoming something we never can be. Space will continue to be explored. Robots will send back images of distant worlds. Telescopes will look deeper into the cosmos. Small research stations will orbit or land on other bodies. And these efforts will expand human knowledge immensely. But we, the complex biological beings that we are, will remain here, in the only place where we can flourish. Earth is not our prison, it is our miracle. It is the only place in the known universe perfect for us, because it literally created us, molded us, made us possible. Every breath you take is a gift of planetary photosynthesis. Every beat of your heart depends on terrestrial gravity. Every thought in your brain requires conditions that only exist here. So, here is the real conclusion, the liberating truth. We will never abandon Earth. And that is exactly as it should be. Our future is not in the stars. It is here, in this extraordinary garden, floating in a vacuum. This unique experiment in complexity and consciousness. Our challenge is not to escape this planet, but to learn to live on it sustainably, to preserve the systems that preserve us, to pass on this miracle intact to futures we can barely imagine. The stars will remain beautiful, inspiring, worthy of study, but home, true home, where every system in your body works as it should, where the air is free and the water flows, where life explodes in infinite diversity that exists in only one place, here on Earth, our only possible home and our extraordinary privilege. And if this journey through the uncomfortable truths of space has made you appreciate the world under your feet more, if it has made you see this extraordinary planet with new eyes, then it has fulfilled its purpose. And if you want to continue exploring the profound scientific truths that transform how we understand our place in the universe, we invite you to stay with us here on Scientia Nocturna, where we will continue to illuminate the wonders and realities of the cosmos, always with honesty, always with awe, because the most important truths are not always the ones that make us dream of distant worlds. Sometimes, they are the ones that help us appreciate the world we already have. The only world we will ever need. The only world that can sustain us. Our home.